let's move on. I have some notes about local density of states. That's what you are actually seeing in scanner tunneling microscope. But let's actually learn what is density of states, what is local density of states, then come back and talk about it, okay? But for now, let's move on to yet another thing that you have heard everywhere: uncertainty principle. So far we have actually explored it a little bit, but now I will give you a formal definition. Let me first of all remind you what commutation was. Commutation was this, right? AB is A times B minus B times A. And when it's 0, we say that two operators commute. When it's non-zero, we say that they don't commute. And we started, if you remember, back in the days when we looked at matrices, we said that this will be the fact that matrices not always have AB equals BA will be relevant later on. Now it is relevant. So the general way of looking at uncertainty is this. Let's say you have operator A and operator B, and sigma A is the variance of the operator A. Okay? You know how to calculate this, right? Given the operator, you can find it. Well, after some math, you arrive at this formula. If you have two operators and you multiply them like this, the amount comes out larger than the expectation value of AB commutator squared. Okay, after some math, this just happens. Okay, well, let's do it. Let's say A is position and B is momentum, and plug it in. Then uncertainty in position squared times uncertainty in momentum squared is greater than or equal to 1 over 2i times expectation value of xp squared. So far, did you follow? Yes? And do you remember what this was? We already did this. Anyone who remembers what? It was I h bar. Right? Do you remember this? You don't? Were you here in harmonic oscillator? Yes, let's remember. Do you see? So we derived it using a test function. So now I can plug it in, and that will give us this. Delta x times delta p is greater than or equal to h bar over 2. It was a bit anticlimactic, sorry. Let me put it in the middle, put it in a box. Yeah, this is what we call Heisenberg's uncertainty principle. And it's a mathematical thing, okay? Because when Heisenberg first came up with it, he had some physical intuition about it. Can you check out what was the year when he started forming this idea? Because I remember that he was trying to convince Bohr with the following example. And now it's a bad example, okay, nowadays. So please don't use it, and I have taught you the right way. Let's go to the wrong way of looking at it. The wrong way of looking at it is that you have a particle sitting there, okay? You want to find where the particle is. So your precision, delta x, is proportional to the light that you are sending in. So you are sending some light to hit this particle, right? And come back and tell you where it is, right? The delta x is proportional with lambda of light, the wavelength of light. So the more precise you want to do it, the lower the lambda should be, right? But if you decrease lambda, you are increasing the momentum, right? Because momentum is h over lambda. So far, so good? Since you are increasing momentum, you are increasing the uncertainty in momentum. In other words, to make a precise measurement, you have to send in high energy photons, which would disturb the momentum information more, right? And that's the physical way of looking at it. But otherwise, it's all mathematics. And hence, it's not about measurement, really. It's about inherent uncertainty in the system. All right? Okay, so let me give you some more mathematical feeling about it. So if you have a wave function like this, we have already seen this, right? If you have a wave function like this, you have a very good idea of what the lambda is, right? It's very clear. It appears many times, so you can know lambda with a very nice precision. You know lambda, hence you know the momentum, right? But what about the position of the particle? You don't know where it is. For x, it's x. Like, do you see? Let me use different color. If you want to measure x, it's that kind of x. Okay. Now let's think about this kind of. Now let's fix x, so that we know where x is. Let me draw it one more time. Okay, this is also bad. No, not even direct delta, but just this much. So now you know where x is. So x gets a green tick. Now you know where it is, right? More or less. But you cannot fit it to any kind of wave, right? So you lose the information of p. Now p gets okay, and for example, what would achieve the lowest value of delta x? So let me give an example. When is delta x times delta p actually equal to h bar over 2? Okay. We had a nice discussion. Do you remember? Let's share that discussion with everyone. Do you remember how we had sort of a free particle? Do you remember free particle in the computer? We would find we would measure its position. But then we would lose all the information about momentum, but then it would spread out, right? So why does it spread out? And if you remember, we said that its momentum functions didn't change. Do you remember that? So we would find this wave, we would construct it by using many different momenta, right? And in principle, the momentum profile would remain the same. So the question that Emin asked is, it seems like delta x is growing while delta p is the same. Do you see the question? No? No one sees the question? Imagine free particle, and we just measured, so it's localized, okay? So it's composed of several momentum that is very, very wide, right? Delta P is high, and it starts propagating, and we have constructed it from energy eigenstates that don't change, so momentum profile doesn't change, while delta x increases. You are not seeing this again? No?
The reason that I think we see some oscillations is because each of these momentum components oscillate in different frequencies.
Yes, but their coefficients remain the same, right? I have constructed them by energy eigenstates, right? And those energy eigenstates don't change with time.
Actually, I think that makes not increasing just because like you need to actually wait for full revolution so that all times are actually aligned again so that we can construct the initial data.
Yes, but presuming that you have enough, you have some reflection, some confinement, right? In this free particle case, it can go on forever. It's just spreading. So the question was, just hear the question, okay? Delta x is increasing while delta p is not going down. And the answer is that it doesn't have to be that, okay? There could be cases where delta x is increasing indefinitely and delta p is the same. Provided that you are above this, you can go as high as you want. It's going low, which is unique. It's hitting that value, which is unique. And you actually do hit this value, delta x, delta p equals h bar over 2. For example, one famous example is harmonic oscillator ground state. So if you take harmonic oscillator ground state, which is Gaussian, right? And find out what is delta x for that, and also find out delta p for that, you are going to see that delta x times delta p is exactly h bar over 2. And this is a very, very nice example to do with raising and lowering operators. It's a lot of fun to figure it out.
Because it's actually related to the coherent state.
How?
Yeah, the eigenvalues of raising and lowering operators, so this is why probably.
Okay, deep stuff that I didn't. Tell me more later, please. But we can actually do this exercise for particle in a box, yes?
Sorry, why the Heisenberg's example is a bad example?
Because it gives people impression that it's a problem with our instruments, okay? It's not a problem of our instruments, it's an inherent uncertainty in the system, whether you are looking at it or not, okay? It's there already in the propagating state when you are not looking. Good? So let's find delta x, delta p for particle in a box. Particle in a box. So particle in a box, you do remember this is the case, right? How would you find delta? Okay, what we are looking for is delta x squared, which is expectation value of x squared minus square of the expectation value of x. Can you tell me what is this? Yes, by looking at the profile, just by looking at this. A over 2. Who said that? Thank you very much. So the expected average is at A over 2. Everybody agrees with this? Yes? And after doing some calculations, you can show that phi star x squared phi from 0 to a actually gives you a squared over 6, 2 minus 3 over pi squared. Okay? Some mathematics have gone into that. And long story short, you keep doing it like that, and long story short, delta x times delta p comes out to be h bar over 2 times square root pi squared over 3 minus 2. And this happens to be 1.136. So it's barely touching it, but it's above it. What is the point? The point is to show you that uncertainty is there. The minimum value can be h bar over 2, but it can be higher. And as you go to more jiggly wave functions, it gets higher and higher. Okay? So you can see that it's connected to commutator, right? When commutator is 0, then delta A times delta B is 0. Do you see that from the formula? Oh, sorry. Greater than or equal to 0, right? Which tells you that you can actually measure precisely one function, one operator, while not failing to measure the other one. So what are the good examples of this? Okay, very good example. But what I have in mind is just a bit easier, but it involves more dimensions. For example, delta x and delta y are like that. Okay, you can measure a particle's x position and y position simultaneously, right? And it wouldn't matter whether you measured x first and y next, or y first and x next. It's very easy to show. Let me show it to you. What is x, y? It's xy minus yx, right? And let's put a test function here. Let me put a test function here. F of xy. So xy minus yx times fxy gives you xyf minus yxf, which is 0. Do you remember why it wasn't 0? Yes, it was like when you have x and p, this one was del over del x, right? Then let's do the following. X, py. What do you expect for this one? 0 again. Why? Let's do it all the way. So there's some function, some test function here, and our operators is x times h bar over I del over del y f minus del over del y h bar over I times x f. You see, this one can actually operate on this one jumping over x, right? It doesn't hit x. That's why both of them, so this one will end up being h bar over I x times del f over del y, and they will cancel each other. Okay? Does it make sense? So you can calculate, measure a particle's x position and y momentum at the same time, but not x position and x momentum. Does it make sense? Yes? When it goes to angular momentum, there are also, like, you can calculate total angular momentum, square, and angular momentum at any direction. And that's why you have L and mz as good quantum numbers for, no, m and mz for atom, right? Very good. Okay. Okay, let's move on. I have covered too much today. There is one thing that is very hard to understand. Very, very hard to understand. Go ahead. You are saying go ahead. We are used to that. This one. Incidentally, what is the unit of h bar? Angular momentum, but also action, right? Isn't it? Joules time second. Not F time, E times T. You see, all this stuff, somehow to me, they connect down there with Noether's theorem, where, do you remember, the symmetry in X would result in conservation of P, symmetry in time would result in conservation of energy, right? And it was all tied to the principle of least action. It's sort of telling me that action is discretized, you know? Something to think about. But coming to this one, this is very, very hard to interpret. So I'm just going to give you the only example that I sort of understand. Okay? No, I don't understand. It's for short-lived particles. When you have a short-lived particle, let's say, can you give me a muon? Muon is a good example, I guess. Let's say you have a detector and you are detecting muons, which live for how long? 20? 2.2 microseconds. Huh? It's just a particle. Okay. 2.2 microseconds? Are you sure? Because it has to come from the sun and there has to be some...
Because of the difference
2.2 microseconds in its frame. In its frame, because it's too fast, it can travel long distances.
Ah, okay. Okay. So some special relativity down there. But in any case, it doesn't live forever, right? So when you measure its energy, you will not always get the same energy, okay? Sometimes you will measure it to have very low energy, sometimes very high energy, sometimes this much. Of course, we are talking about rest mass energy, right? Like m0 c squared of the particle. If you calculate that, you will get this. And basically, this is delta E, and it's the amount of time that it lives is delta T. And if you multiply them, it's around h bar over 2. At least it's higher than that, for sure. Okay? All right. We have 20 more minutes. Why? We have 20 more minutes. So many things. Let me actually move on to quantum mechanics. In 3 dimensions. So far we were doing it in 1 dimension, right? So let's do it in 3 dimensions, and the Schrodinger's equation just simply extends to 3 dimensions like this, x, y, z. Now you have a wave function that depends on all 3 coordinates, and the kinetic energy simply extends to a Laplacian, right? Oops. And you have some 3-dimensional potential, and then you have wave function that also depends on 3 coordinates, right? So we have moved from del squared over del x squared into this one. Yes. Okay. Do you have any objections to this at this moment? Yes? No? So you simply extend the ideas into 3 dimensions. For example, particle in a 3D box. What will happen to this one? Well, let's imagine that box. Let's put x, y, z here. And you have your box here. It has a length a in x direction, b in y, and c in z. Do you understand the system? Everyone? Yes? So inside the box, the potential is 0. Outside the box, the potential is infinite. So it's confined inside it. In 1 dimensions, you would get h bar squared pi squared over 2 ma squared times n squared. Do you remember that? That's energy. This is the energy of the system. And it would depend on a quantum number, right? Do you remember that? So it was E, 4E, 9E, and continues like that. Now this time in 3D, it will depend on 3 numbers, 3 quantum numbers, because it's quantized, it's not quantized, it's confined in 3 dimensions. The x direction, y direction, z direction. So you will actually have, let me just point out this section. So this is the important part. Actually, not even the pi squared, just this part. So for each direction, you will have n squared over a squared. Okay, actually let me do it this way. Let me do it this way. This was coming because you had h bar squared over 2m del squared over del x squared. That was corresponding. This would turn into n pi over a squared. Do you agree with that? Yes? Now you have all three of them, right? 1, 2, 3. So the energy is going to be dependent on three values: E and X and Y and Z is h bar squared over 2m times nx pi over a squared plus ny pi over b squared plus nz pi over c squared. So confinement in 3D, confinement in 3D, confinement in 3D leads to three quantum numbers. Let's look at a simpler case where we don't have like A, B, C, different stuff. Let's look at a cube. What are the energies of a cube? So a particle in a cube with length A in each side.
Will it be really simple?
Hmm?
Will it be really simple because you have these vertices?
I mean, like at least you don't deal with A, B, C. Like each part, let's say this is A, and this is A. So what you have is h bar squared over 2ma squared, even pi squared is here. So it has nx squared plus ny squared plus nz squared, right? So it will have the ground state energy of this will be when nx equals to 1, and y equals to 1, and z equals to 1. Then you have a function that goes like this here, and like that here. No. You can't have. Can you have 0, 0? Yes, of course. Of course. That's right. It's not the ground state. Sorry. You actually can have this. So it's like bumpy on one side, the other sides are just blank. Let me think about it. This is right? Do you have any objection to this? Are you following at all? Yes? But ground state is degenerate. What does it mean, degenerate? It means that different functions correspond to the same energy. So nx, ny, and z being 1, 0, 0 gives you a function that has dependencies on nx, ny, and nz. Let's call it 1, 0, 0, which leads to energy E1, 0, 0, which is simply h bar squared pi squared over 2ma squared. But there is another wave function which corresponds to the same energy, right? It's like 0, 1, 0, E 0, 1, 0. And what is the energy of this one? Same. If you remember, that's why I was confused. we're not allowed to have 0 before in one dimension. Now we are allowed to have it. Now why is that? It's three-dimensional. It's enough for just one of them to have a bump, right? But 0, 0, 0 is still not allowed, right? Very good, very good. Okay. So do you have any questions? I think in previous years I actually started from 1, 1, 1. One generation of students. Okay, I don't think it's a big deal. Yes, yes. Do you have any questions, comments? We still have 10 minutes. Hmm?
There is an option.
Let's solve the hydrogen too.
Yes, you have a question.
I checked, there is no 0 for the ground state. It's not degenerate.
What do you mean?
Like, it starts with 1 for all the constants. So the ground state is not degenerate.
Are you sure?
Yeah, I checked it right now. I'm not sure it's correct, but
Why 1, 0, 0 wouldn't be a solution?
so it should be somewhere.
Ah, okay, yes. Okay, so the problem is that it has to be 0 everywhere. So if it's like this, right? If it's like that, you are not making it 0 along this boundary over here. Did you follow this? Did anyone follow this? No? Okay. Okay, let me tell you. There you go. Thank you very much. Now we can fix this. So, no, we start with 1, 1, 1, and let me tell you why. I'm glad that we did this mistake. So you have to start actually with this. And it's non-degenerate. And it starts with 3. And there is no such thing. Let me tell you why. So what you want to have is you want to have the wave function go to 0 at each boundary. So it has to be 0 over here at that boundary. It has to be 0 over here at that boundary. Okay? That's the z boundary. And it has to be 0 over here on the whole place. So what is wrong by having just sign on one side and 1 on the other sides is that it doesn't go to, it does go, if you have something like this, phi 1, 0, 0, it does go to 0 over here, it does go to 0 over here, okay, but it doesn't go to 0 on these other faces, on these faces. It needs to go to 0 in every side of the cube, okay? Am I confusing you? I don't trust you anymore.
Ben de şimdi okudum makaleyi de şey, it's because like if you write the full wave function, it's sine n pi x pi
Yes.
of a,
Yes,
sine n pi n y pi of a, y.
yes.
If you make n y and z zero, whole thing wave function becomes zero automatically, no matter what the x is.
No. Like this corresponds to some coefficient times sine pi x over a, right?
Pi x and x.
Yes, and x is 1.
Yeah.
The
Just write the general form.
you are writing the general form and you are putting ny and nz to 0 and
Just
It
Kill
does
the other terms automatically.
disappears. Yes. Did you understand this? No? Let me so let me write you the general form. I actually do have it here. The general form is this. So square root 2 over a, square root 2 over b, square root 2 over c. You multiply them all together, right? And you get nx pi x over a sine ny pi y over b sine nz pi z over c. Okay, and if you put any of these to 0, the whole thing just becomes 0. Does it make sense? I was talking about it as if when you put it to 0, it's still just 1, but it isn't. It's just 0 everywhere. So let me erase this part. And this is your answer. Thank you very much. So what is the first excited state? This is the ground state. The first excited state is degenerate, and it's composed of E211, E121, and for the cube, by the way, for the cube. You will have 1, 1, 2, and they will all have how much energy? 6, right? 1 plus 1 plus 4 h bar squared pi squared over 2 ma squared. Okay?
Hocam bu mesela sınavda nasıl gelir? Ben çözümünü verseniz aynısını yazarken kesin hata yaparım ben. Kağıttan kağıda geçirirken yanlış yaparım.
The question is, how would it appear in the exam? First of all, these parts will not appear in the midterm. You know that, right? Yes. You will have a cheat sheet, right? A one sheet where actually in the final you will have 2. So you can bring 2. You can write the whole thing down. What kind of a question can there be? For example, there is a cube in there is a particle in a cubical box. Write down second excited state, energy of a second excited state. Is this hard to?
Which one is the second? Yani hepsini kim yapacağız onları?
Okay, very good question. So you start with 1, 1, 1, and that corresponds to 3, right? Then first excited state is degenerate. There are 1, 1, 2, 1, 2, 1, and 2, 1, 1, right? Which is 6. What is the next excited state? Is it 2, 2, 1 or 1, 1, 3? Do you see the dilemma there? So 1, 2, 2 would give you 1 plus 4 plus 4, which would give you 9. 1, 1, 3 would give you 1 plus 1 plus 9, which is 11. So the second excited state is 1, 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 1, and it's 9. It's like that. That's the end of the question. Yeah.
Bu mu yani bu kısım? Bunun devamı.
The exam is composed of tiny questions and mid-sized questions. We will talk about the exam extensively next week. So next week, it's the review week. We go over the whole material that will appear in the exam and over the previous exams so that you get the feeling about the exam.
Jim, what was the last topic on?
quantum harmonic oscillator included. Any other questions? Okay, let's stop here.